Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving a locus problem. So we have the absolute value of z over z plus 2 equals 3, and we're going to find the set of z values that satisfy this equation. I'll be presenting two methods, but first let's talk about where this problem comes from. This problem was suggested by Bobby Heffley 4955. Thank you for the suggestion. I think this is a great problem. Let's go ahead and see how we can solve it in two different ways. All right, let's start with the first method. We have the absolute value of z over z plus 2 equals 3. Now, what kind of complex numbers can satisfy this? First of all, one of the things you can think about is, does z have to be non-real, right? Or what happens if z is real? You can go ahead and solve it. But that's only going to give you a small subset of the solutions. We want to find all possible solutions, and I'll show you how we can represent them at the end. So with my first method, I'm going to do the following. Replace z with a plus bi. And when I do that, it's going to look like this. A plus bi divided by a plus 2 plus bi, because I'm going to increase the real part. And then I have to absolute value this, and that's equal to 3. How do you find the absolute value of this expression? First of all, you may want to, just make the bottom part real by multiplying by the conjugate. So let's take a plus bi, a plus 2 plus bi, and then multiply these by a plus 2 minus bi and a plus 2 minus bi, the top and the bottom. Now, from here, you're going to get a somewhat complex expression, or should I say complicated. You can go ahead and distribute. You get a squared plus 2a, and then from here you should get plus b, because negative, actually b squared, negative b squared I squared, and then you should be getting something like minus ab, and then plus a plus 2 times b, minus ab, and then all of that is multiplied by I. And at the bottom, you're going to get sum of two squares. Remember the formula, when you multiply two conjugates, you get the sum of two squares. And then you have to absolute value this, and that's equal to 3. Make sense? Yes, this kind of complicates things, but again, that's the first method. Now from here, let's see what we can do. We have a complex number that is divided by a real number. So we can actually think of it this way. We can separate it into real and imaginary parts, like a squared plus 2a plus b squared is divided by a plus 2 squared plus b squared plus a plus 2b. By the way, when you distribute this, you're going to get ab plus 2b, or not 2b, minus ab. ab is going to cancel out. You're going to end up with 2bi. So let's go ahead and write it that way. 2b, and that'll be divided by a plus 2 squared plus b squared. And then that's multiplied by I. You're going to absolute value that, and that's equal to 3. So it's a little easier because we kind of wrote it in standard form, right? So this is the real part, this is the imaginary part, and we need to square those, add them up, and square root, and that's equal to 3. If you want, you can square both sides. That'll give you a 9, and so we're just going to add the squares. So we get something quite complicated from here, which is going to look like this. Let's write it down. By using the definition of absolute value, this squared plus this squared is supposed to equal 9, because it's the square root, right? Makes sense? So from here, you're going to get something quite complicated, and then you need to simplify it, right? So you're probably thinking there must be an easier way to do this, and let's talk about it, which is actually the second method, okay? So the second method obviously simplifies things. That's why it's important to know these properties. Let's say you didn't know that this property existed, you would probably use the first method, but it will be painful. So it's worth knowing. So the properties of absolute value. One of them is, if you have the absolute value of z1 over z2, it's the same thing as absolute value of z1 over the absolute value of z2. Obviously, z2 should not be 0, right? So we can go ahead and separate it. And is that going to help? Yes, a great deal. So we're going to get absolute value of z divided by the absolute value of z plus 2 equals 3. Now, since z plus 2 cannot be 0, we can go to multiply both sides by its absolute value. That's going to give us absolute value of z equals 3 times the absolute value of z plus 2. Awesome. Now, what does this mean though? We still need to go through the absolute value, but it's a lot easier. Take a look. We replace z with a plus bi with the first method. So why not do something slightly different, and let's replace z with x plus yi, right? So if you do that, you're going to get x plus yi. So it's going to be x plus 2 plus yi. When you take the absolute value, this is going to be the square root of x squared plus y squared. And then this is going to be the square root of x plus 2, which is the real part, squared, plus y squared. Awesome. What would you do to get rid of the radicals? Square both sides, right? Let's do it. If you square both sides, you're going to get x squared plus y squared equals 9 times. Now this expression, you're going to get rid of the square root, but let's go ahead and expand these. This is going to give us x squared plus 4x plus 4 and then plus y squared. And then we can go ahead and distribute the 9. If you distribute it, we're going to get 9x squared plus 36x plus 36 plus 9y squared. Now, it would make sense if you had everything on the same side, and obviously we want to use the positive side, right? So, subtract x squared, you're going to get 8x squared. Subtract y squared, you're going to get 8y squared. Let's write those first, okay? So we've taken care of those. And then we have already on the right-hand side, plus 36x plus 36, and this is equal to 0. Awesome. Where do we go from here? So here's one thing you need to do. Look at the coefficients of x squared and y squared. They are the same. Nice. Is there an xy term? No. That's also nice. Extra nice. So consider this as a conic. It will be something very special. Let's go ahead and find out. I want to go ahead and first divide both sides by 8 so that I can make the coefficients of x squared and y squared 1. And then we're going to get 36 divided by 8, which is 9 halves, right? And this will be 9 halves again. Awesome. And this will be 0. Great. Now what can I do with this? Complete the square and get the sum of two perfect squares. So let's go ahead and put the x squared and 9 over 2x together. Think about what you would add to both sides to get the perfect square. And that can be found by using this coefficient. Half of 9 half is 9 fourths. If you square 9 fourths, that's going to be not 36, obviously. 9 fourths, 81 over 16. So that's what you need to add to both sides. But of course, you can't just add it. You also have to subtract it. So our equation is balanced. Awesome. And guess what this is going to give you? A negative term, which you need to put on the right-hand side as a positive term. Great. Everything is working fine. Now we have the following. This part is a perfect square. Guess what that is? X plus 9 over 4 squared. And this is y squared. And this expression on the right-hand side is going to be 81 over 16 minus 9 halves, which is actually multiplying by 8 gives me a 72. Subtract from 81, it gives me 9 over 16. Beautiful, because that's a perfect square too. So in other words, if you consider the equation x minus h squared plus y minus k squared, and that is equal to r squared, this means it's a circle with center h comma k and radius r, right? So this is a circle because the coefficients of x squared and y squared are the same, and there's no xy term. If there's an xy term, then we're in big trouble, right? So this is going to be a circle. So in other words, the locus is going to be the circle. Now, if you check Wolfram Alpha, it's actually going to give you interesting results, and you can kind of tell me what that means. For example, first of all, if you graph it as a real function, it's going to look like this, right? There are some intersection points, as you can see, which kind of tells you what is going on. Well, Wolfram Alpha says a real solution, at least one of them, is -3 halves, and the bottom one is an interesting one. What is that supposed to mean? Anyways, this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.